Thank you, Melissa. It's an honor to be here amongst bird watchers. So, this is a cartoon image of my enthusiasm for the Aurora and everything else Alaskan. I had Jamie Smith, the cartoonist, create this for me a couple years ago, and I just love it. This was a friend of mine, a pretty good birdman, Spike Baker, who this kept coming up to Camp Denali, and he finally got the picture of the Aurora that he was trying for about 3 or 4 years in a row. And this is one of his pictures in a calendar he sent me. This is the these are my crib notes. The smallest bird in North America, measuring about 3 inches long, weighing about 1/10 of an ounce. Despite its tiny size, it's able to survive cold winter nights at high elevations in the northern Rockies, and some migrate every year from Canada all the way to southern Mexico. In migration, it may be overlooked, often feeding at low flowers and avoiding the aggression of larger hummingbirds, and it's from Idaho. So our videographer here tonight, Ron Murray, is from Idaho, I think, or at least he spent some time down there in southern Idaho. Ron took this picture, really beautiful. Love having something in the foreground. It's a great way to take photographs, to have something in the foreground to give you a sense of size and scale, and a little moonlight really helps too. This was a recent launch out of Poker Flat. It was the only photograph that I've included with regard to the rocket range and what we do with launching rockets to study the auroras, but it's such a good photo that I thought I'd better make it a part of tonight. But there are 4 actual rockets launched there. You see the first stage rockets burning and pushing up. They actually have burned out at this stage, but they're still hot going over the top, and you can see a couple of them have hit the ground out here. Then these other 4 marks up here are the second stage rocket motors pushing the payloads up higher, and then 2 of the rocket payloads carried chemicals that they dispersed in the atmosphere. And those are like putting food coloring dye in a large sink to be able to watch what the patterns of the motion of the winds and things are, or the water in the sink, but the things in the atmosphere. You can tell this is a single picture with multiple openings and closings of the shutter. That's where you see the stars forming these tracks across and around. And the beam that arches over across the top there, that was a heart of the experiment. It was involving a laser system at Poker Flat called a LIDAR that was actually making measurements in the atmosphere. And then in conjunction with that, once they got the situation and determined it with the LIDAR that it was worth investigating for the kind of winds and turbulence up there, then they launched the rocket program, a hugely successful program. There were 5 rockets launched in the last couple of weeks. This was one series. All these launched within about 30 minutes. And then a couple nights later, they managed to get the next one up and out. So way back when, people thought that God just put this dark bowl over our head at night, and it had holes in it, and what you saw were not stars. They didn't know what stars were, but rather they were the lights of heaven streaming down through the holes. But occasionally there became breaks in that bowl or chasms. So once you go back in history from about 1,500 back to 4,000 years ago, you'll find a pretty good description of chasms of light in the sky, and the other information that goes with them makes us think we pretty well know what they were talking about was an aurora. Galileo Galilei was the one who decided that it sort of looks like the Roman goddess of dawn, that being in the early morning when the sun is coming up, you can see the light, the red light streaming through the atmosphere, through the gaps in the mountain passes, and that would be the goddess of dawn. The term borealis, we never did figure out exactly when that got added to it. In general, it means northern, etc. This pretty well tells you the whole story. Auroras are caused by events on our sun, and it blazes an electrical and magnetic storm out through space towards the Earth. The Earth, you probably have seen the little picture of the magnetic field of planet Earth with it's almost perfectly symmetrical off either side, sort of like when you have a magnet and you have iron filings and you get a pattern like that. But in the reality of this, the storm particles, as they come towards the Earth, they compress the magnetic field on the side of the Earth next to the sun, and they expand it out on the way on behind. Also, the particles, the storm from the sun can't get to the Earth, but is shunted around the Earth, and those energetic particles actually come in from behind the Earth and create the auroras that we see, much stronger on the night side, midnight sector, and it's a process very much like the neon sign. So it's an electrical storm coming into the Earth's atmosphere. It's causing the atmosphere components themselves to give off light, and there is an aurora borealis and an aurora australis in the Earth's atmosphere. So what do you need? Three things. Our star is a pretty typical, but it has storms. You have to have a planet that has a magnetic field, and you have to have a planet that has an atmosphere, and then you can have auroras. This is a little NASA animation showing that storm coming in, sweeping around, snapping, coming in from the rear, and cascading down to create the auroras that you see. This is from the International Space Station coming up on Chicago and the Great Lakes and going up the St. Lawrence Seaway. They have beautiful views of the aurora. Part of the space station hanging up there above you. So Galileo Galilei, again, was the one who saw that the sun had blemishes on it. And in addition to being blemishes, they slowly moved across the sun, and he determined that this meant that the sun rotates on its axis. These things would go across in about 2 weeks and then would disappear and then pop up on the other side again. So he was the first one to figure this out. He saw the blemishes on the sun. We now say we call these sun spots. And the more spots you have on the sun, likely the more auroras that we're going to have here on the Earth. They follow a 22-year cycle, which also looks like an 11-year cycle. And in that, the storms start out near the polar regions on the sun, and they sort of drive out of the center through the polar regions. And the Earth is right around the equator of the sun, so most of those storms do not create auroras on the Earth, but we end up with them over time with the storms coming closer and closer to the equator of the sun, and we end up with more activity, and we're sort of at the top of that right now. This is where we are in our current cycle of activity on the sun. It has taken a steady downhill run the last 2 solar cycles, and this one has been a lot weaker too. It's been amazing to me that we've had as many auroras as we have this fall and winter. It's just been a fabulous time for auroras. But not super great ones, but a lot of them. This is what you see in the Fairbanks Daily News Miner, or you see on the website at the Geophysical Institute at the University of Alaska. This is a level 2. I think 2 nights ago it was level 4. That meant that it even went much further south than that. It covered the whole state of Alaska. But we're sitting here at one of the prime places in Alaska for people to see the auroras. There's something they call a 27-day cycle in which the sun turning on its axis and the Earth going in orbit around the sun. Every 27 days we line up again. These storms on the sun can actually last several Earth months. So once that sunspot activity gets going, it may last quite a while. And this is a good thing to look for. We'll often have 2 or 3 or 4 nights of really good aurora in a row, and you want to be watching 27 days later because the chances are you'll have good auroras again. So can we predict the aurora with a solar cycle of 11 years, all these various maps with a 27-day repeat, or is it a crapshoot? Well, I created this. This storm on the sun comes out with a big wad of energy headed towards the Earth, and that energy has both an electrical charge and a magnetic field associated with it. And so what will happen is that thing is tumbling like a tumbleweed as you come through space. I think all of you know that if you ever played with magnets, the way you really get the most energy coupled between 2 magnets is if they are opposite to one another at the last little bit, and that's the case here. So you never know what that's going to be. It's a crapshoot at the last minute. If that part of the storm as it hits the Earth has that blocking with the same polarization, with a north here and a south up there, then even though it's been a tremendous storm, we don't get the coupling that we would have, and we don't get much in the way of an aurora. But when you do get this thing coming in this way, then you actually couple up the magnetic field lines, transfer the energy, and away you go, bringing it in behind the Earth in large amounts, which then it sneaks in from the backside and creates what we see for the aurora. And I already showed that slide. So on day 0, the sun has a storm. It takes about 2 days for that storm to physically traverse from the sun to the Earth. It's real physical particles. It's not 8 minutes like you've often heard about. The sunlight takes 8 minutes to get from the sun to the Earth. This takes a couple days for these things because they're real physical hardware things like electrons and protons. So Jupiter's about 6 times further out, and we see auroras on Jupiter about 12 days later. It's got a magnetic field. It's got an atmosphere. 24 days later, we see an aurora on Saturn, just like we did. And so we see auroras moving throughout our solar system from close and around the Earth, throughout all the planets. The Earth has the best and most beautiful in comparison with what a human being can see, but these happen on these other planets because they're all gas giants with magnetic fields. This is a, in honor of Spike again, this is a little hummingbird out of Peru. Figured you guys would be good for a laugh tonight on this. The old coquettes spend very little time in the forest and instead feed on low-flowering plants around shrubby clearings, roadsides, of the forest edge. Their flight is rather bee-like, and individuals tend to favor high perches. So, you didn't expect that, did you? For a long time, we were pretty well convinced that the auroras were identical in the northern and the southern hemisphere. It took us a long time to prove it. It was pretty sketchy until we got a chance to get up in airplanes and fly simultaneously in the northern and the southern hemisphere and map our positions with respect to the Earth's magnetic field. The first experiment that really defined it was in 1967. It worked so well with black and white film that in 1968 we got color film and got an images here on the left of the aurora over the top of Fairbanks. On the right, the magnetically conjugate, the magnetic field in Fairbanks ends up about 750 miles south of Christchurch, New Zealand. And it looks like it's a mirror image, like pages in a book. You could just flop that thing on the right over the top on the left. We found the next year with television cameras that the auroras were identical to one another within a fraction of a second. If one moved a little bit, the other one moved correspondingly. If one changed in brightness, the other one changed in brightness. So it was pretty cool stuff. 1974, was a military satellite program polar orbiting the Earth that created some of the imagery that you've probably seen more recently, where you see the street lights of East United States and Florida, the core of the United States, the western coast of the United States, the Edmonton oil fields, and way up there, Alaska, and so on. But it takes about 90 minutes for this satellite to orbit the Earth. And in its first run over from north to south, it was probably around midnight. And it saw this kind of aurora. And then this was probably an hour and a half later, around 2 o'clock in the morning. So you ended up with a really great broad aurora in the sky. And then an hour and a half later, another orbit coming over the top. The aurora had quieted down. And then the last picture in the upper part, then you probably had a little sunlight starting to scatter in the atmosphere to illuminate the ground. By 1985, we worked with NASA to build a satellite that could see the aurora during the daytime as well as at night. This is not anything you could see with your naked eye. This is actually light that is invisible, so ultraviolet. But what they've done is make it appear with yellowish thing. It's the light of atomic oxygen, and this was the sun causing the atmosphere to glow. That would have been high noon. This would have been the transition from day to night. This would be the aurora in the sky, and again, that would be the midnight sector. We always saw this. You might think that maybe the aurora is going to come south to Fairbanks tonight. What's really going to happen is Fairbanks is going to turn underneath this aurora. It's not that it's coming so much as we're going to go under where the aurora normally is. This is an electrical light pattern in the sky that's there all the time, 24/7. Admittedly, this does change when you have a really powerful set of storms on the sun. This whole circle that you see here, this crown of light on planet Earth, can get much bigger in diameter, and we will maybe not even have any auroras visible in Fairbanks, Alaska, and it's all down over San Francisco and Texas and places like that. That can happen. It did in March 13th, 1989. This is over Antarctica. The aurora is mostly out over the ocean. That's the Antarctic continent. There are research stations in Antarctica. By and large, in the northern hemisphere, you have a lot of land mass from 45 degrees north almost to the North Pole where all the auroras are, and everybody gets a chance to see them. The southern hemisphere, 45 degrees south, is still offshore between Australia and the South Pole. So you just don't get much of a chance to see them. There are some auroral research stations in South Island on New Zealand and Tasmania for Australia. And what they usually see is something way to the south and usually get radar signals rather than visible sightings of the aurora. But again, this is that picture from the side with the aurora over the southern hemisphere with Australia and New Zealand, Hawaii, and the arc of the Aleutian chain up there. So roughly speaking, the aurora is from about 50 to 120 or 150 or so miles above the surface of the Earth. The reason we see it is that it finally gets bright enough that our eyes can pick it up. And it gets brighter and brighter as it comes down, and then it kind of snuffs out along the lower border or edge. That's the brightest part of the aurora. Doesn't get down any further into the ozone layer, does not get into the weather. The aurora stays up pretty high. The people that have been in the International Space Station or the people that have been in the space shuttle can actually fly through the aurora. They're not allowed to get out in their spacesuits and do extravehicular things because their spacesuits do not protect them. It's a real low level of energy. Auroras are not very powerful. They're really not much more powerful than a neon sign voltage, 20,000 volts or something like that. But what you would end up with is sort of what you have when you go out in the mountains, or if you're around on the summer days not wearing a sunblocker, you can end up with some genetic damage in the surface areas of your skin. And that's what the astronauts in their spacesuits are still, they're not protected well enough by the spacesuit, but inside of the shuttle or inside of the space station, they're fine. A lot of things happened when we got film, and by that I mean glass plates, back around 1890 to 1900. For the first time, identified where the aurora was in the sky above the ground, because prior to that, they didn't know if it was flowing in from outer space or was it swamp gas coming up from below. But now they identified it in the sky as a physical thing and get the altitudes with simple triangulation. Here at the University of Alaska, we had a station out near, camera station, out near where the city dump is today, and another station on the university campus. And we were really ahead of the time. We used radios to communicate back and forth because there was no telephone lines connecting those sites. And with those, we were able to tell people when to open up the shutter of the camera and when to close it. It takes 8 minutes then to register the auroras. Those photographic plates are at the Museum of the University of Alaska. This turned out to be an experiment driven by the idea, is the aurora in Alaska the same as the aurora in Norway and Europe? They were the pioneers who did the triangulation on the aurora, and we followed it up over here. Now, with hours and hours of exposure and a little simple prism, we're able to finally register what the colors of the aurora were, and darn if they weren't identical to what had been done in laboratories on the surface of the Earth, taking air apart and then electrifying it and causing it to glow. So with that, we found that it was a neon sign type process, and in comparison to the spectrum of sunlight, which is pretty uniform from blue to red and green, the aurora has some green, then there's nothing until you get way out in the red, and nothing until you get way down in the blue. The human eye is far more capable of registering green than it is red or blue. So by and large, people tell me, well, I didn't see any color, but it was kind of white. Well, that's kind of what the eye tells you. But then when it does get brighter, then you see it's green, and when it really gets bright, you see the blues or the reds. If we could see equally all colors, blue and red and green, the auroras would be far more fantastic, and they have a lot more of the red that we just don't get to see. So here's that little spectrum now blown up, and I've added to it the human eye response. So you can see we're pretty bad about seeing the reds and the blues. And if you're colorblind like me, then you really have trouble picking out the reds. So this is kind of what you see. A weak aurora at the top, a moderate aurora, you'll start to pick up the other colors. If you get a really bright aurora, then you'll get that. Finally, see the whole thing. It's a little tough to see this. This was 1958. It took nearly 8 minutes to get this registration of red. The aurora, blood red aurora, is a very rare thing. It only happens a couple, 3 times every 10 years. And it happens up very high in the Earth's atmosphere. And it's because the electrons have been banging into oxygen atoms and giving off the red light. When you see a blood red aurora like this, it does not have the structure, the vertical bars, the motions. It just looks like a blob in the sky. On the other hand, it looks like the gods are fighting and they're spilling blood all over the place. The other colors we see from the blues come from molecules of nitrogen, the greens from oxygen, and down along the bottom in this slide, they called it crimson. So this is Neal Brown's version of this. Again, when you have a blood red, it's very high, and it's all atoms of oxygen. The Earth's atmosphere, where you and I are breathing right now, are molecules of oxygen and molecules of nitrogen. A molecule of those are 2 oxygen atoms to make a molecule of oxygen, and 2 nitrogen atoms to make a molecule of nitrogen. And the air we breathe is roughly 20% oxygen and 70% nitrogen, and that's the case all the way up into the aurora. But as you go up higher, the air gets so thin that all you have are atoms way up high. So now we get this block of green much lower in the atmosphere of the aurora. Then we get these vertical, I didn't check this with my wife, I hope that's blue or purple. At upper range around 120 miles, 200 kilometers. Then we get what I call magenta along the bottom, fleeting magenta. Usually it's got a lot of fast motion in it. And it comes from molecules of oxygen and nitrogen. And the base of that's around 60 miles above the Earth. So here's a picture of that green blob in a little bit of the ray motion. You really have to get dark adapted to go out and see the aurora. If you walk out of a brightly lit room or you're watching TV, you don't stand a prayer. It takes about 15 or 20 minutes for your eyes to relax so you can really see something in the sky. And the auroras are rarely brighter than the stars you see in the sky. If you can see the double star there in the handle of the Big Dipper, you can see the whole Big Dipper, and you can see those double stars, then it's usually dark enough for you to be able to get a pretty good rendition of the aurora. And again, this is kind of a sequence of what you see. Early evening, no structure at all, but some sort of glow across the sky. Then by getting closer to midnight, you're starting to see some vertical structure in the aurora, maybe a little motion, maybe not. But right around 1 o'clock in the morning, you're starting to pick up some color along the lower border, some bigger motions of this whole thing. And then around 2 a.m., what we call breakup, the aurora for about 10 to 15 minutes can just become really dynamic, really blazing, bright colors, very, very fast motions. That's what a rayed arc looks like in the sky. These are actually the magnetic field lines of the Earth. I'll wait to get back to that. I love this place. This is Patrick Anders, Mount Sukcapak. If you go up north of Coldfoot, then there's this great mountain that you look at from the north coming south that has this great, you're looking south into where the auroras typically occur. It's a really dynamic mountain. Kind of interesting from the southern side, too. Now, there's another little Peruvian hummingbird. Marvelous spatulate is a medium size, up to 15 centimeters long, with white, green, and bronze hummingbirds found on the forest edges in Peru. And he can move those little spatulas independently. It's a crazy little hummingbird. So, anciently, people thought that somehow or other the magnetic and the compass that you had was attracted to maybe something way out deep in space like the Polaris. And it was William Gilbert who took a very simple magnet and made it so it was perfectly balanced. And then when he moved from like England to Norway, he saw that the change in it indicated that the magnetic field of planet Earth actually comes from inside the Earth. We don't totally understand what causes it, but I do want to just throw this other little tidbit out. The idea that you have a compass that points towards the north, you call that tip of your magnet in your pocket, your compass, the north end of the compass, but you all know that it's only going to be attracted to a south pole, so the north magnetic pole on planet Earth is really a south magnet. So this is kind of where we are here in Fairbanks. The Earth's magnetic field here would be straight up and down at the pole, but we're far enough away that it's kind of tipped at 13 degrees. That means when you look up in the sky, the auroras straight up over are going to be kind of long, but when they get about 13 degrees south, you're looking right up through the whole line of the aurora, the thinnest part. And this is a little device that you can use that's three-dimensional magnetic probe. And if you take that out at night and hold it up, you'll see it lines up perfectly with the rays of the aurora in the sky. They're lined up with the Earth's magnetic field. You see the same thing from the shuttle. You can see this red. There's always red up high. It's not always bright enough for you and I to see, but once you're out in the shuttle or something like that, it's very dynamic. Does the aurora make sounds that you and I can hear? I think we've all been somewhere where somebody was hammering on a peg, and then we were far, far away, and you can see that they hit the peg, but you also know it takes time for that sound to get to you. It would take about, people report sound being synchronized with what they hear, with what they see, but at the speed of sound, it would take about 9 minutes for the sound of the aurora to get down to us here. So that's the big question that we don't know how to answer. Some people report that it's sort of like a buzzing electrical sound. Other people have reported it's sort of like a fire. In general, the reports are that it's an exceptionally clear night, very, very clear, and that the aurora seems to be very bright and trying to race past itself in the sky. And during those conditions, they hear a sound. Now, one person may hear it perfectly. The person standing beside them may not hear it at all. So we think more it has something to do with the person, and it's maybe not their hearing, but it's something else going on, because the idea of that simultaneous sound being heard with the motion of the light doesn't make much sense. We've never been able to successfully record the sound of the aurora. We've tried in various ways, and we just never had any luck doing it. So how do you take a picture of the aurora with a camera? This is a relatively simple $700 camera and a $700 lens on a tripod, because you're going to have to take a picture that's about 10 seconds long, f2.8, and you want to set the ISO for something like 800. Do not want to have any filters on your lens. People put filters off on camera lens to protect them from getting banged and bumped up. You want to take those off, because in a long duration exposure, you can often end up with some circular patterns, interference patterns. Another thing you want to do, just because you're mucking around out there at night in the cold, is put a piece of tape to hold that thing to make sure it's locked in on infinity and doesn't change on you. A lot of modern DSL cameras, their lens systems are such that they always automatically find focus, and they can't do that on stars and the aurora. They just can't cope with it. So if you're going to go out and take pictures of the aurora using the kit lens that the camera often comes with, you just about have to find where that is perfectly focused during the daytime and lock it down with a piece of tape. There are other ways to do it, but that's one way to do it. The other thing to minimize bumping the tripod when you're taking the picture is to either set your camera on one of these things where you can punch the button and run around and get in the picture yourself. So you got 2 seconds or 10 seconds or something like that. Or you can use a simple little electronic control, something like that. But this is kind of a minimal system. It's actually a Tokina lens, which is really wonderful in that when you get it, when you set it for infinity, it's there. You don't have to muck with it at all. It's a really super lens. This was set up on the Mount Sikupak with a tripod system, looking at it from the north during the daytime. Your camera is going to work just fine for the most part. The weak element in it are the batteries. They tend to crap out when it gets cold, but most DSLRs will function just fine. But when you go to bring them back in, a nice bitter cold 40 below camera, or even just a cold camera, when you bring it in a room, it's going to, all the moisture in the room, the humidity, your breathing and everything else are going to glom into and often can get right inside and create problems with them. So much better if you put it in a blanket, put it in a bag. I went over to Sportsman's Warehouse or something, whatever it's called, and they had a bag of desiccant, kind of a huge thing there. But the nice thing about that bag of desiccant is I can take it and put it in my oven and revitalize it, you know, bake the moisture out of it. So, but that's a way to keep your cold soak camera, let it warm up slowly, make it so it doesn't suck up moisture. Hope this comes through. I got permission from Ron Murray and Marketta to show you this video. It's about 2 minutes of real time. These colors are real. When you take a picture for 10 seconds or so with a camera, you actually can get pictures that you can't see with your naked eye. We took the first video of Aurora's broadcast quality in 1985. The camera cost $1 million. It's defunct today. The camera system here, altogether, right around 10,000, more or less. By the time you add all the bells and whistles to it, it might be more, but it's amazing what is available today. I wanted to show this 29-second clip also because here you can see some of the fast motion that you can see with your naked eye that you'll never get with a photograph. It just can't, that's moving too quickly. But that's real, that's what it really looks like. Amazing. I always duck when someone says, what causes all that motion in the sky? It really starts about 200,000–300,000 miles away from the Earth and then creates what we see here. It's sort of like you standing in Tucson, Arizona on a big sheet of pavement in front of you on a hot day, and I'm standing behind you with a water hose, and I'm streaking water over your head, and I can write my name on the sidewalk in front of you, and you can ooh and all you want, but I'm the one that's doing it way back behind you. And that's what the Aurora does. It's far, far away from the Earth that sends all that towards the Earth, shapes it the way we see it, and we don't have a clue. We have been playing and trying to understand that for a long time, but it's very hard. So Ron has a website. You can use Ron Murray, pretty much his name with 2 N's, and you'll get to the website. He does have a webcam that you can go to and see what's happening in real time. Then a couple of years ago, Patrick Anders put together an ebook on how to photograph the aurora. And I was asked to write a foreword for it, and I ended up writing a little bit more and put it in. That's my only writing. Neal Davis is really well known in this community, and his books are still out there and amongst the best for anyone to read and learn about the aurora. I get up and talk and yammer and so on and so forth, but I haven't written much yet, so maybe someday. Dr. Agasafu has written the Northern Lights book. I think about every other year he's issued a new version of it and added more to it. It's always good. But I like Neal's book for the solid links in the science. Now here's the real heart of tonight's talk. You'll really have much better chance of seeing the aurora if you do this. And
Am I understanding correctly that if I were standing under that sheet, that would be the swirls?
yes,
Then that I see when
right,
as the earth rotates and
right,
gets underneath those
right.
sheets?
Yeah, very much so. That's what you're seeing there. It would be like standing underneath and seeing those swirls happening in real time over your head. Just amazing. Human eye is just absolutely great, and you do get to see this with your eye, and yet when you go to take a picture with 10 seconds with, now the human eye is like a 1/4 inch in diameter entrance aperture, and it takes a picture in 1/10 of a second. Then the electromechanical system takes another picture, swapping out the chemicals and getting the So now compare that to a 3-inch diameter photographic lens in 10 seconds, and even though the sensor isn't as sensitive as the human eye, you will see colors that you just don't see with the naked eye, particularly reds up high. Yeah?
I think you said that you haven't figured out how to record sound.
Right.
Is it a sure thing that sound is part of an aurora experience?
It doesn't always happen, but it does happen fairly often. We probably get, I still get 10 or 20 reports of it. Hunting season every year. People go out hunting and they talk about what they heard and when they heard it, and they were so far away from any sort of power or any other noise that wasn't the case. But there has been a paper published and video on YouTube about the auroral sound, and they say they located it like 300 feet above the ground, but it's clapping. And I don't know anyone that has ever reported to me clapping sounds. And they have the sound that they say they got in Finland or Northern Europe, I forget where it was, but it just doesn't fit with what I've experienced. So, yeah. Yes?
Could you go back over again why you see the northern lights brighter around midnight shooting than earlier in the day?
Right. So the real bulk of that energy that can create the aurora has been swept around the Earth by the Earth's magnetic field. It's gone way behind the Earth, and it's really on the anti-sun side where it's sort of stored. And then it loads up enough that it kind of breaks loose and comes forward. It's almost like thinking you loaded up a rubber band so much the rubber band breaks. And now it kind of accelerates that energy in towards the Earth. It accelerates some of it away from the Earth, but accelerates some of it in towards the Earth from the rear. And that tends to be strongest at in the midnight sector. Now, 2 a.m. is more the time. So what it really is for you and I, 2 a.m. is when you can draw a line from the sun through us to the magnetic pole on the other side of the world. So that's 2 a.m. it's different for wherever you live on planet Earth. It would be a different time that you'd have that strong pulse of coming. But that, in general, that's it. A question that no one has asked, but I'm going to jump in anyway, is there's no aurora over the polar caps. And over the Antarctic center or over the Arctic center, there's no auroras. To have an aurora, you actually have to have connected field lines between the northern hemisphere and the southern hemisphere, and they kind of load up, and the stuff bounces back and forth and drains out each time to create those multiple images that are identical to one another, that brighten at the same time, that move at the same time. And that doesn't happen because the magnetic field lines up around the north part of the pole, they are swept back and broken loose, and they're kind of waving out in space. And so are the ones from the southern hemisphere. They're not connected solidly between the two hemispheres. So that's why there are no, everyone used to think if you went to the North Pole, the aurora would be even better than, but no, it's really in that crown of light surrounding the magnetic pole of both the north magnetic pole and south. Yeah.
So the north and south are always identical or sometimes identical?
Always identical. They start to deviate from one another when the auroras get super duper moving and bright, and I think they still are identical, but here's the complicating factor. As long as there isn't much going on, the two magnetic the magnetic fields in the two places are mirror image to one another, and you can do a calculation on a program and send an airplane to those two locations. When we did this, when the aurora started to really crank and get really bright and move, we could watch from the airplane that magnetically conjugate place was moving away from where it should be. That's because the aurora was creating a magnetic field locally at altitude, 50 miles above the Earth, that was causing it to be slightly different than it would be by just making the formal plot. And so we couldn't keep up with it with the airplanes. It was moving too quickly. But we watched it get away from us. And so, yeah, there is that. But then that's really bright. But by and large, when you see that early evening aurora, they're pretty identical. And one brightens, the other one brightens, and when one moves, the other one moves. It's really amazing. More questions?
Talk about what happens to other planets.
Sure. The auroras on Earth are very dynamic and respond to these storms coming in the way that I've shown you here. The storms on Jupiter, which is bigger, has more magnetic field and has more atmosphere, are much bigger and stronger than they are on Earth, but they also have a peculiar situation that the satellites that orbit, like Io and close in on Jupiter, they generate, in the midst of that, they generate their own little storm that creates a dot of light in the northern and the southern regions of Jupiter. And it's about 3 of these things. That one, you have the general aurora like you do on the Earth, but it tends not to have the ring. It tends to be right in the top. And then it's got these little arcs running around it where you see the pattern and labeled as to what satellite of Jupiter. The same thing is true of Saturn. It has a smaller, in comparison to the physical size of the planet, to the auroras in the cap, not so much a circle. So all the gas giant planets, Uranus, Neptune, all have aurora much like we see them on Jupiter and Saturn. That is, magnetic fields, atmospheres. The atmospheres on those planets is primarily hydrogen. These are old gas giants, so they don't have all the chemical components the Earth's atmosphere does. And so the auroras on those planets tend to be blood red, real dark reds. And they do create some other light that you can filter for the Hubble Space Telescope and see the auroras very easily. But to the human eye, it's really on the ragged edge of red colors. If you have your telescope at home and get a really good look at Jupiter, you probably won't see the auroras, but you do see them with the Hubble Space Telescope. And then a few years ago, we had a lot of fun with the idea that, you know, the Earth's atmosphere is out of chemical balance. We got all this oxygen, and oxygen just loves to make everything rust. And it, of course, makes us the fuel that we need to move around and everything. So the Earth is out of chemical balance, and that's a good thing for us. But it would also mean that if we're looking out there with a Kepler Space Telescope and we're trying to look at other planets in our universe to see if we can find something that might be habitable like Earth, if we found a planet that had auroras on it, then we could say, then it's got, and the aurora has oxygen in it. They say, well, that makes it even a more likely candidate to be like the Earth, that we could, there might be a habitable life forms out there. We're very egocentric that way, though, you know. All right, well, she said I had till 9 o'clock, but I'll take pity on everybody. I'd like to thank you for coming out for the Audubon Society. If you don't know much about them, they're a really good organization. I was a little bit involved watching how they were doing, what do you call it, when you capture the birds and mark them and keep records on them. Yeah, so that's been done here in Fairbanks. It's also done out near Camp Denali in Denali National Park. And it's a fascinating thing to watch how the birds are captured and very carefully taken care of and get back up and fly away and come back 2 or 3 years in a row to the same place. Fascinating subject. And bird counts in Christmas time, probably heard of those things, so not a bad thing to get involved with Audubon. All right, thank you very much.